25. Tajemnica. Przed nami główne wydarzenie, główny wykład trzeciego dnia festiwalu, ale zanim przedstawię naszą gościnię, niech mi wolno będzie powiedzieć, że partnerem Copernicus Festival jest Małopolska Organizacja Turystyczna, która objęła patronatem dzisiejszy dzień festiwalu poświęcony tajemnicom kosmosu. Projekt jest dofinansowany ze środków budżetu państwa przyznanych przez ministra nauki i szkolnictwa wyższego. Dofinansowano go ze środków ministra kultury i dziedzictwa narodowego pochodzących z Funduszu Promocji Kultury Państwowego Funduszu Celowego. Partnerem wydarzenia jest miasto Kraków. Copernicus Festival został także objęty honorowym patronatem ministra nauki i szkolnictwa wyższego oraz prezydenta miasta Krakowa Aleksandra Miszalskiego. Jak już wspomniałem, przed nami główny wykład tego wieczoru. Jest z nami profesor Ruth Durer, która jest szwajcarską kosmolożką pracującą na Uniwersytecie w Genewie. Profesor Durer specjalizuje się w badaniu mikrofalowego promieniowania tła, wielkoskalowej struktury wszechświata i ciemnej energii, a także wielu innych aspektów, wielu innych tajemnic wszechświata, o których nam za chwilę opowie. Jest także członkinią misji Europejskiego Teleskopu Kosmicznego Euclides, który od 2023 roku obserwuje odległe gromady galaktyk, mierząc szybkość rozszerzania się wszechświata w ciągu niemal całej jego historii. Mamy nadzieję, że pozwoli nam to lepiej zrozumieć zagadki ciemnej materii i ciemnej energii. I o tych zagadkach między innymi opowie nam profesor Durer w wykładzie pod tytułem Mysteries of the Universe. Professor Durer, thank you for coming and the floor is yours.
Thank you very much for the kind introduction. Thank you all for coming and sharing with me the next hour where I want to talk to you about the mysteries of the universe. Sorry that I cannot talk to you in Polish. I just don't speak your language. But also English is for me a foreign language, so we are probably all used to it, and you can listen in the translation if you don't speak English. So I assume that you know very little, if not nothing, about cosmology, and I want to share with you some of the things I'm very much excited about it, and especially things which we don't understand. I will first introduce, give an introduction to the talk, and then talk a bit about the size of the universe, because I think it's sometimes good to remember what vast distances we are looking at when we want to study the entire universe. Then I will talk about the expansion of the universe. How do we actually find out, or did we find out, that the universe is expanding, and how can we study how it expands? And then I will come to a cosmological standard model which we have developed over the last 20, 30 years, and that will already be it. I don't know why we have this strange thing here at the bottom. I don't have this on my screen. Let me maybe just, yeah. Anyway. Sorry about the bottom. I don't know what that is. I don't have that on my screen. Anyway, we always wondered about the universe around us, right? How large is it? What is it made of? Was it always the way it is now, or did it evolve? For a long time, such questions have been addressed by mankind using myths and stories, and actually Karl Popper, the scientific philosopher, said science must start with myths and with the critique of myths. Actually, only with Einstein's theory of gravity, which he also called general relativity, did cosmology, which is the science of the universe as a whole, become a true natural science. Let me explain a little bit why this could not have been done earlier. When the theory of gravity was Newton's gravitational theory, it was impossible to describe a universe permeated with matter that would have led to singularities in Newton's theory, to an infinite gravitational potential, and one could not determine actually the gravitational potential in such a situation. Einstein realized that immediately, and already a year after he published his equations of general relativity, he came up with the first theory of cosmology. He wanted a static universe and introduced already the so-called cosmological constant, about which we will talk more during today, in his first solution. You only can get a static solution if you introduce such a constant. But now I don't want to talk more about that. I want to talk about distances. Let us start with the radius of the Earth. It's about 6,000 kilometers, as probably most of you know. And the first, actually, that I would know, determination of the circumference of the Earth was quite surprisingly performed already by Eratosthenes before more than 2,200 years ago. And he gave the following arguments which led him to a very good estimate of the circumference of the Earth. He realized that at the longest day of the year, 21st of June, the sun shone vertically into a pond in Syene, today Aswan in Egypt, while it made an angle on a vertical stick of about 1/5 of a circle. This is about 7.2 degrees in Alexandria. Now, the distance between Syene and Alexandria was known. It was about 5,000 stadia, which are about 800 kilometers. So a 50th of a circle, of the circle around the Earth, is therefore about 800 kilometers. 800 times 50 gives 40,000 kilometers for the circumference of the Earth, which is quite precise. So that was already the ancient Greeks who knew that. And I think it's quite surprising that they could calculate this so precisely. And later on, they used this distance to infer via other clever methods, for example, the distance to the moon and the distance to the sun, with more or less successes. But let's not dwell on this anymore. Let's go further. The solar system. Solar system is about 7 billion kilometers, a 1 with 9 zeros. If there is an index on a number, like here, this 9, it means a 1 with as many zeros behind it. Because if these zeros become too many, we don't write them out. Otherwise, we always have to count these zeros. It's getting complicated. This distance, the light takes about 6.5 hours to traverse this distance. This distance is also called 50 astronomical units, where the astronomical unit is the size of the Earth's orbit around the sun. That's an astronomical unit. Now let's go further. The closest star, our sun is a star. Which star is next to us? It's actually Alpha Centauri, which you see here with the red arrow, indicated with the red arrow. It's Proxima Centauri, a neighbor of Alpha Centauri in the southern sky. We don't see it here in the north, which is about 4.2 light years away from us. So you see it's already 4 times a 1 with 13 zeros in kilometers. This is also 1.3 parsec. Parsecs are an important distance measure in astronomy, which is defined as follows. If we have here the Earth orbit, the Earth orbiting around the sun, And let's say in spring we are here, we see this source over there in this direction. And in fall, when we are here, we see it in this direction. So there is a difference between the direction at which we see a faraway source in the spring and in the fall. And the angle, the distance of if the angular the angle between these two directions is 1 arc second, which means 1 degree divided by 3,600, then we call this distance 1 parsec. And so the closest star moves a quarter of a second from spring to fall. And this distance corresponds to about 3.26 light years. So the light from the closest star to us takes more than 3 years to arrive. Now that's all inside our own galaxy, inside the Milky Way, right? The visible part of our galaxy is about 10 to the 18 kilometers wide, which is 30,000 parsecs. So 1,000 parsecs are also called a kiloparsec, so that's about 30 kiloparsec. That's just the visible part of our galaxy. This galaxy, of course, is not the Milky Way, but it's a galaxy that looks similar to the Milky Way. The Milky Way, we cannot see it like that because we are sitting inside it, right? We cannot look at it from outside. Now we go to the universe. Here you see picture from the DESI collaboration. DESI is the Dark Energy Spectroscopic Instrument, the big telescope sitting in Arizona. And this collaboration has measured the spectra of several million galaxies, about 10 million galaxies. Each point on this plot is one galaxy. The colors here are false colors, of course. The galaxies here depicted in blue are the so-called bright luminous galaxies. The ones in yellow are the emission line galaxies, and the ones in red are the luminous red galaxies, because we see those further out. When we go further out, we look mainly at those. The size of the observable universe is about 4,000 megaparsecs, so it's about 4 billion parsec, which corresponds to about 13 billion light years. That's the time light takes to traverse the universe to us. And it contains about 100 billion galaxies, like the Milky Way, and many more smaller galaxies. So it's just huge. Now, nearly 100 years ago, Edwin Hubble has measured the radial velocity of galaxies and the distance of these galaxies and the radial velocity relative to us. How can one measure this radial velocity? You remember probably if you have, for example, a motorcycle, a loud motorcycle passing by, when it approaches you, the sound goes up and then it goes down. It makes something like when it passes you, right? So when it goes away from you, its sound becomes lower. And this is the so-called Doppler effect. With light, we have exactly the same thing. If a light source goes away from us, its light is shifted towards the red. We call this the redshift. It's indicated by the letter Z. And if the velocity is much smaller than the speed of light is about 300,000 kilometers. So it's about nearly 8 times around the Earth in 1 second. That's the speed of light. So it's very, very fast. So if the velocity is much smaller than that speed, the redshift is given just by the ratio of the velocity divided by the speed of light. If the velocity approaches the speed of light, the formula becomes more complicated. So he has measured this redshift. How did he measure that? We know spectral lines in stars. We know, for example, the spectral lines of Lyman alpha transition in hydrogen, or some helium lines and carbon lines. We know exactly where these lines, at which wavelengths they are in the laboratory. And if we see them at the redder wavelength in an object in a galaxy far away, we know this galaxy is receding with a given velocity, and we can estimate this velocity. And he also had ways to estimate the distances. I will talk about this a bit later, but let's just take it for a given right now. And he found that the relation between these two, the velocity and the speed, is actually linear. That's what we call now the Hubble-Lemaitre law, because the person who first actually published this relation here was Lemaitre. He published it a couple of years before Hubble, also using Hubble's data. Here is the same graphic much later, where I want to show you something. Now in the horizontal axis here, you see the redshift. And in the vertical axis, you see a kind of a logarithmic measure for the speed of expansion. If the speed is constant, you would be at 0 here. If the speed is lower in the past, here you go below 0. If it is larger in the past, you go above. And these are data points. I will talk about these data points more in a second. And you see, they show us that the speed of expansion is actually accelerated right now. Then it turns over to a constant, and later on it decelerates, it goes down, so it becomes smaller again. So presently it looks like the expansion of the universe seems to be accelerated. Why is this interesting, or why is this bizarre? Gravity, as we know it, is an attractive force, right? If we let something fall, if we let loose of something, it falls down to the Earth because of the gravitational attraction of the Earth. I think nobody has ever seen a stone or left loose a stone and it went up. But that's what the universe does. So we would think gravity is attractive, so the matter in the universe should break the expansion of the universe, should make it slower and slower and slower. And it actually looks that it does quite the opposite. It makes it faster and faster and faster. How can this happen? In Einstein's theory of general relativity, this can actually happen, but only if you have energy density and pressure density which is such that the pressure is very, very negative, such that that the pressure is nearly as negative as the energy is positive. Because within general relativity, what makes the gravitational attraction is the sum of the energy density plus 3 times the pressure. In normal matter, as we know it, we can usually neglect the pressure. Or if it is anything, it is positive. Pressure is positive. But there can be situations where pressure is negative. For example, if we have vacuum energy, the pressure is negative and is actually equal to the energy density, but negative. Or also a cosmological constant acts exactly like vacuum energy. There is no experiment which can distinguish between vacuum energy or a cosmological constant. So we shouldn't distinguish between them as well. They are one and the same thing. Now, to get this blue curve, which is shown here and seems to be in reasonable agreement with the data, we would need that 70% of the expansion is due to such a dark energy component with a strong negative pressure, and only about 30% is due to matter. Now, how did one obtain these points? One needs to measure the expand, yeah, maybe I'll come to back to that a little bit later. You see there are black curves which are due to supernovae, and I will talk about that in a minute. And then there are the red points which are due to baryon acoustic oscillations, which I didn't explain yet, but will explain a bit later. And these baryon acoustic oscillations, we see it by looking at galaxy surveys like the one of DESI. Here you see even newer data, the so-called Pantheon Plus compilation of more than 1,000 supernovae, 1,500. Now we have even more, and data will become even more precise. But even here you see the upper curve just shows you a measure of the distance with, so this vertical quantity mu here is a logarithmic measure of the distance to an object, while the horizontal axis is again the redshift. And this curve here is the best fit model, where again this dark energy with negative pressure contributes about 70%. And you see this model is in good agreement with the data. Here is the measured value of the distance minus the value of the model. And only at very small redshifts it doesn't work out. And we understand that because there are velocities of the galaxies which do not follow perfectly the expansion, and that at small scales makes deviations which we do understand and are no surprise. As I already told you, the redshift is this Doppler effect for the light. What you also have to be aware of is that in cosmology, when we talk about the entire universe, looking far always means also looking in the past. I mean, even the people here in the first row, if I look at them, I see them the way they were a couple nanoseconds ago, because that's the time light takes from the first row into my eyes. But this is not interesting because people don't change in the time of nanoseconds. However, if we look out in the universe, we see things how they were billion years ago. Already our neighbor galaxy, the closest big galaxy to us, Andromeda, if we look at it, we see it the way it was about 2 million years ago. For a galaxy also, this is no big time, 2 million years. The galaxies live billions of years. But still, in cosmology, this is an important point. If we look far, because we don't only look to our neighbor galaxies, we see many galaxies. If those which we see really far away, they are really characteristically different. They are irregular. One sees they are still forming. They are not yet as nice spiral galaxies or elliptical galaxies as most of the galaxies in our neighborhood. They are really of a different type. A moment in the past, as we have said, is a moment at a given distance, and the distance is related to the redshift. So usually in cosmology, we indicate moments, times with the redshift of that time. And we have seen that the recession velocity, the velocity of galaxies, is proportional to their distance from us. If we don't go too far away, afterwards there are corrections. To measuring redshifts is relatively easy. We can measure them looking at the spectra of galaxies. However, measuring distances is very difficult. There is an entire story. I could talk an entire evening about how wrong distance measurements have led to mistakes in astronomy. For example, did you know that already the Greeks had a Copernican view of the solar system? Already the ancient Pythagoreans said that the sun should be in the center and the earth rotating around it and the other planets. But people said, no, this cannot be right. This must be wrong, because if the earth would be rotating, we would see the stars in a different direction in fall than we see it in spring. This is true, but they have completely underestimated the distance of these stars. The distance of the stars is such that even for the closest star, this difference in direction is about a quarter of an arc second and couldn't be detected until Bessel in the 19th century, who was the first to actually measure this so-called parallax effect. So then they said, okay, yeah, that's an argument. So the Earth must be in the center and must be at rest. But the only the error in this argument was that they didn't. They underestimated the distance to the stars, and so on. But okay, so how do we measure distances? There are two main methods in cosmology to measure distances. One is with so-called standard candles. If we know the intrinsic luminosity of an object, then via the flux which we receive in our telescope, we can get its distance. Now, there are several objects in the sky of which we know their intrinsic luminosity. For example, there are the so-called Cepheid stars, which are pulsating stars, and their period is very closely related to their redshift. And measuring this period closely related to their luminosity, measuring this period luminosity relation inside our galaxy, and assuming it's the same in other galaxies, we can measure the distances to many, many galaxies. This was the method which also Hubble was using. Now, another standard candle are supernovae type 1a. There are several supernovae, but the type 1a are probably all so-called white dwarfs which go over their mass limit, the so-called Chandrasekhar limit, and explode. So it's always the same physical phenomenon that takes place, and therefore they have always nearly the same luminosity. There can be slight differences because the composition of the white dwarfs can be slightly different, and they can be in different environments, which can also have an effect. But we can correct for that. And so one could gauge this luminosity of supernovae by supernovae which we have in galaxies where we also see Cepheids. But since these supernovae are so luminous, we can see them much, much further out. And these are kind of these prominent standard candles which led to all the black points which I've shown in the previous diagrams. Another method are so-called standard rulers. If we know the intrinsic size of an object, then if we put it far away, the angle which it subtends in the sky is actually proportional, inversely proportional to the distance. Far away objects are seen under a smaller angle in the sky, whereas closer objects of the same size subtend a larger angle in the sky. So do we have objects of which we know exactly their size? Not truly, but we have a so-called statistical standard ruler, which are the so-called baryon-acoustic peaks, about which I will talk in more detail just a little bit later. And these were the red points which I showed you. Now let us talk a moment about the thermal history of the universe. I said the universe is expanding. In the past, the universe was not only much denser, but it was also much hotter. As you can imagine, if you press something together, it heats up. And actually, now the universe is close to 14 billion years old, but when it was only 400,000 years young, it was so hot that before electrons and protons could not combine to neutral hydrogen, and the universe was charged. But then when it cooled to this to about 4,000 Kelvin, that's about 4,000 degrees Celsius, close to 4,000 degrees Celsius, finally the temperature was low enough that the photons wouldn't kick out all the electrons from the atoms, and the atoms could combine into neutral hydrogen atoms and neutral helium atoms. And at that moment, the universe became transparent. The photons or the light particles in the universe would just traverse it more or less unimpeded or nearly unimpeded into our telescopes. That moment is called the recombination. Even earlier, when the universe was only about a couple minutes old, nucleosynthesis took place, which is the moment where neutrons could bind with protons into so-called deuterium, heavy water, sometimes also called. And then two deuterium atoms would immediately get a helium atom, which is much more stable. This, at this moment, during this nucleosynthesis, more or less all the neutrons in the universe were burned into helium. And already Gamow in the 40s could calculate the abundance of helium in the universe by doing this calculating what happened in the early universe. And this explained why the abundance of helium in the universe is quite universal, the same everywhere, whether there are lots of stars or not. Heavier elements like carbon, iron, oxygen have been formed in stars. And even heavier elements than iron have been formed in supernovae. So you all contain material which has gone through a supernova. So, and of course, you contain a lot of material which has gone through stars. So you are all stardust. Even earlier, there might have been phase transitions in the universe. We don't really know. In the standard model of particle physics, maybe not. But if there are deviations, phase transitions might have happened. But what we have relatively good indication is that at some point a so-called period of inflation took place. We don't know when it took place, but if we have such a phase of very rapid expansion, first of all, it makes a universe which is on very large scales, nearly homogeneous and isotropic. But it also leads to very small fluctuations, and these fluctuations are actually quantum fluctuations, which are amplified because they are ripped apart, and then they are just staying there because they are no longer in causal contact, that they could go back into the vacuum state anymore. And one can calculate the spectrum, so the amplitude of which such quantum fluctuations should have on different scales in the universe. And one finds that they should have roughly the same amplitude on all scales if such an inflationary phase took place. And what happens to such fluctuations? That these are fluctuations in the energy density in the universe, and correspondingly via Einstein's equation also in the geometry of the universe. Very small fluctuations. I will show you how they can have been found in the cosmic microwave background. But first I show you the so-called spectrum, namely the brightness as a function of frequency of this cosmic microwave background. Underlined in pink, you see a thermal spectrum at the temperature of 2.728 Kelvin, which is about minus 270 degrees Celsius. And you see that's a very good fit to this data. All the blue points here are the data from the COBE satellite, from the FIRUS experiment on top of the COBE satellite. And actually, this spectrum is a perfect thermal spectrum with no deviations as far as we know. It's actually the best spectrum at this temperature which we have. We cannot produce something as good over 3 orders of magnitude in the lab. That's the limitation which we have so far for the measurements of this spectrum. But this cosmic microwave background, this background radiation is not only very thermal, so very good in thermal equilibrium, but it is also very isotropic. Isotropic means the same in all directions wherever we look. Here you see the sky, so-called Eitov projection of the sphere around us. The top figure is just the mean temperature, and you see it's very, very homogeneous. If you subtract the best fitting constant, you get the second diagram, this one. And what you see here is what we call a dipole. It's hotter on one side and cooler on the other side. And this is exactly what happens if we move through this sea of radiation with a constant velocity. And we need a velocity of about 300 kilometers per second to produce this 1,000th dipole which is seen here, and that is probably our velocity with respect to the sphere at which from which this radiation is emitted. If one now also subtracts the best fit dipole from this radiation, one ends up with the third picture. Here the fluctuations are only 18 microkelvin, so really small. Here we were at millikelvin, here at Kelvin. So what you see mainly is this red band through the middle, but that's just our galaxy. The coordinate system is chosen that our galaxy lies here in the equator, in these so-called galactic coordinates. And our galaxy, of course, also emits in this wavelength, in this gigahertz wavelength, and it's actually the dominant source only once these monopole and dipole have been subtracted. Here you also see a little bit of the galaxy, if you look closely. But even if you don't look at places where the galaxy is, you see something, you might say, okay, that's the noise of the instrument, but no, it isn't. It was a real detection which has been awarded by the Nobel Prize in 2006 and which has been confirmed tremendously later on. Now the picture corresponding to the lowermost map of the sky looks as this. That's the microwave sky as seen by the Planck satellite. Once the dipole has been subtracted and a fit for our galaxy has been subtracted. We want to learn something from these fluctuations. How do we do that? We analyze them by computing the so-called spectrum of fluctuations. This means we calculate or we average over little patches of a given angular size, let's say 1 degree, and we average the mean square amplitude of the fluctuations on a given angular scale. We do that over the entire sky, and then we take another angular scale and do the same for it, etc. And then we get a spectrum, and that's how it looks. What you see here dominantly is these so-called acoustic peaks. What are they? If we have initial fluctuations from inflation, then the moment these initial fluctuations come in causal contact, they start oscillating like sound waves, because the gravity pulls them together, but the pressure, the radiation pressure, pulls them apart again. And the first peak here are fluctuations of the size which had just one time since the period of inflation to contract together. And the second peak is an underdense peak where fluctuations have been put together and gone apart again, etc., etc. This also measures very well the baryon density in the universe, because the baryons, the ordinary matter, protons and electrons, they are tightly coupled to the photons before this recombination process. And they are more heavy and they don't really have much pressure, so they prefer collapse under gravity than expansion. That's why this first peak is so much higher than the second, which is an expansion peak. And the third is so much higher than the fourth, which is again an expansion peak. This damping envelope here, we also understand it. This blue curve here, through this data, was done just assuming that we parameterized the initial amplitude of fluctuation, the initial spectrum from inflation, the amount of baryons in the universe, the amount of dark matter, and the amount of dark energy, and maybe spatial curvature. So we have some 6 numbers which we have to measure via these curves, but with these 6 numbers we can fit data which contain more than about 3,000 or 4,000 numbers, because there is not only this temperature spectrum which I'm showing you here, but there is also a spectrum of the polarization of this radiation, etc. So here there is something which we really know. And the interesting thing is that these acoustic peaks which you see here, they also show themselves in the same kind of spectrum of the distribution of galaxies, which, for example, this DESI, this dark energy spectroscopic instrument, has measured. And that can then, here we measured this acoustic scale at which these fluctuations are. That's exactly the sound horizon at the moment of recombination. Afterwards, baryons and photons decouple, so this sound horizon is also in peak. That's our statistical ruler, because this is a statistical quantity, right? The mean of the fluctuations over a given scale all over the sky. It's a mean, it's a statistical quantity. We do the same with the galaxies. And we see the same kind of sound horizon also there. And we use this as a statistic ruler that made these 3 red points, which you saw 15 minutes ago or 20 minutes ago. Okay, what is the result for the parameters which we can measure with this data? What is their contribution to the expansion of the universe? Ordinary matter contributes about 5% at best. Very, very well constrained with very small errors, you see here. Dark matter contributes about 27% to the expansion of the universe. And the lion's share is contributed by the so-called dark energy. If this dark energy is vacuum energy or a cosmological constant, for me these two are synonyms, then the pressure, this P denotes pressure, is minus the energy density. Rho stands for energy density. And this explains, if that's true, why the universe is accelerated. So this data, like the supernova distance data, also wants a universe which is where the expansion of the universe is accelerated now. The spatial curvature is compatible with being 0. The initial spectrum from inflation has an amplitude of about 2 times 10 to the minus 5, so very, very small, as you see, 4 zeros after the comma, while the spectral index is nearly scale invariant. The definition is such that if here there would stand 1, this would mean that the fluctuations are the same on all scales, same amplitude on all scales. Here, this is a little bit smaller than 1, which means the spectrum is a tiny little bit red. Fluctuations are a little bit larger on large scales, but it's a very small effect. That's the result from the cosmic microwave background mainly. Now, if we take the DESI results, which came out only about a month ago, in April this year, they combined their standard ruler, which they have at different redshifts, out to redshift 1, in about 6 different redshift bins, with data, either the cosmic microwave background or different supernova data. Here they used different combinations of supernova. The one I showed you, the latest one was Pantheon Plus, but they also used other data, Union 3, DES 5 years, and they always also used the CMB. Without using any other data, they could not come to this strong conclusion which they have brought about here. But this if we look at this diagram, it looks like, hey, WO equals -1 and WA equals 0, which is the cosmological constant. That's that point out here. Seems to be excluded. What they show here is the highly, the strongly luminous part is with about 68% confidence the data should indicate this region. With 95% confidence, it shows the larger, more extended region for omega A and omega naught. Here the ansatz was made, just some simple formula, that omega depends on redshift, so it's dynamical. W being the relation, the ratio between the pressure of dark energy and the density of dark energy depends on redshift. They assume it is some constant and then some redshift dependent bit which vanishes when redshift vanishes. But this constant seems to be less than -1. And this redshift dependent bit seems to be substantial. For me here, I would say it's early days. We are not sure that there are no systematics in this data which we didn't account for. I hope this is right, but I wouldn't bet on it at all. We have seen bigger effects and they have gone away with more careful data analysis. You see, we have lots of things in cosmology which don't quite agree. We are used to data which has systematic problems which are not really taken care of, and so it looks very interesting, but I would want more data before I would bet on this. But more data is coming, more supernova data, but also this supernova data might have systematic problems, but also more data from our statistical standard ruler, the baryon acoustic oscillations, and from other probes of the universe. For example, just to tell you that there are most probably, and we know it, problems in this data. For example, if this data is also very sensitive to the mass of neutrinos. Neutrinos are very elusive particles, but in the universe there are billions and billions of that. Actually, in each centimeter cube, there are about 200 of these neutrinos in the entire universe. So the expansion of the universe is also sensitive to those. And we know that they have a mass via, for reasons which I could explain to you. But let's just say we know that they have a mass, but we don't know what this mass is. We don't know the mass scale. And if we try to measure the mass with this data, we obtain a negative mass squared. a negative mass. Sorry, we obtain a negative mass, which we know is not physical. So there are systematic problems still in this data. And this data is new and it's difficult to analyze, and we will have to work more on it. But still, we hope to have discovered something, and maybe we do. But let's also wait for the Euclid satellite, which was launched about a year ago, and which will give even better data than DESI. It has the advantage of being a satellite, so it doesn't have to fight with the atmosphere and with weather and all that. So it can take very homogeneous data, which is the same all over. And we are really looking forward to get this data. First data was actually already coming out, but that was not yet data which was useful for cosmology. It was useful for other astronomical purposes. But certainly in a year from now, we will really know more. Okay, that's already more or less all I wanted to tell you. I'll come to my conclusions. As I have told you, the universe is expanding. In the past, it was hotter and denser. This fact is supported by many different observations, by the Cepheids, by the cosmic microwave background, by looking at galaxies which are further away, which are different from galaxies which we see now, etc. I think people working in cosmology, there is nobody doubting that anymore. In the past, the universe was not only was dominated by ordinary matter and by dark matter, and if we go even further into the past, it was dominated by radiation. Since the radiation photons or so lose energy due to the expansion, their wavelength, which is inversely proportional to their energy, expands as well, so they lose energy. So they dilute faster than matter does. And that's how the universe became matter-dominated. But also matter and radiation have either non or positive pressure, so they always lead to a decelerating universe. However, since about 6 billion years, it looks like the universe would be accelerating. So the expansion presently seems to be accelerated. So the universe is dominated from a dark energy component, which seems to have anti-gravity, so makes gravity, instead of attractive, repulsive, something which we don't know from our experiments on Earth, from our surroundings. There are many different models of dark energy, but none of them is theoretically convincing. Is it the cosmological constant, which would also be vacuum energy? If that is true, we have to explain its very, very strange value. A value which is more than 60 orders of magnitude smaller than what you would naively estimate for vacuum energy. And so before we measured the accelerating expansion of the universe, we always thought there must be some reason coming probably from quantum gravity that vacuum energy does not gravitate, does not contribute to gravity. The first who was actually hypothesizing this was the famous physicist Wolfgang Pauli, who said if the vacuum would gravitate and we cut off quantum theory at the electron mass, the universe wouldn't even reach out to the moon. Or is it a dynamical dark energy, like from a scalar field or so? This actually doesn't seem to agree very well with this DESI modelization of dark energy, but as I said, this data is very preliminary. Another piece which many of us actually pursue is, might it be that general relativity breaks down on cosmological scales? most physical theories are valid on a certain range of scales, and then they change, or other effects come in at larger or smaller scales. For gravity, we know this must happen at very small scales, the Planck scale, but that's a very, very tiny scale. Might it be that this also happens on very large scales, on cosmological scales? We don't know it. With the new observations like the DESI one, which I have already indicated here, or with the Euclid satellites and other stage 4 surveys like the Vera Rubin telescope, or the so-called SKA, the Square Kilometre Array, a radio telescope which is being constructed in South Africa and in Australia, we really want to address this mystery of dark energy. And with this, I thank you for your attention.
Thank you very much for this very interesting talk. I mean, cosmological constant dark energy is one of the biggest mysteries of the universe, and from your talk I got the impression that it gets even more mysterious with time. And we will address these questions, these ideas for what dark energy might be in the discussion that will follow this lecture. But right now, since we're already running out of time, let's allow Professor Dürer to have a short break, and then also you will be able to ask some questions during our discussion, which will begin shortly in about 15, max 20 minutes. So please stay with us, and let's thank our speaker again.